few more indefinite integrals to look at. I cannot do this one in its current form because it's a product, but I can expand this product first and then I'll be able to integrate it. So I want to integrate from 4 to 1 of, and this is going to be x minus 4 minus x squared plus 4x dx. I'm going to rewrite that a couple times. The first thing I will do is just reorder it, so the negative x squared is first. We have a plus 5x, and then we have a minus 4. Okay, now one of the things that pops out at me right away is that the bounds are in the opposite order. It's usually lower than upper, and they're swapped. So I could swap them back to 1 to 4 by applying a negative, and then we can distribute that negative. So this is going to be negative the integral from 1 to 4 of the same thing, of x squared plus 5x minus 4 dx. I saw those opposite bounds, and so I switched them into the standard order by applying a negative, and so I can distribute that negative and now be from 1 to 4 of positive x squared minus 5x plus 4 dx. So we didn't do any integration yet, but we've gotten this rewritten a few times, and so when I integrate it, it's now got standard bounds, and I can integrate it piece by piece. Okay, now we'll begin the integration step. So we'll integrate the x squared into x to the third over 3 minus 5x, so 5x squared over 2 plus 4x bounded between our bounds of 1 and 4. So we'll plug in top bound. That's going to be the 4 cubed minus 3 minus 5 times 4 squared over 2 plus 4 times 4 minus the 1 cubed over 3 minus 5 times 1 over 2 plus 4 times 1. Okay, so we're just going to calculate this. I can use the Desmos calculator, and we'll check it after we have gotten a little further. But for right now, I just want to evaluate the fractions. So 4 cubed over 3 minus 5 times 4 squared over 2 plus 4 times 4 minus a third minus 5 halves and plus 4. Okay, so I should be able to stretch this out so I can see a little bit more of what I've typed there and verify that everything looks okay. And then if we want it in fraction form, we can get the fraction form of negative 9 halves for our answer. Negative 4.5 is fine since it was non-repeating, but the exact value, again, negative 4.5 or negative 9 halves. Okay, now if we check it, we can do the integral, int, and it was between 4 and 1. I can type it in any form, including the original. So I'm going to use parentheses, and then I'm going to do extra parentheses just to make sure everything's inside that integral. So parentheses, 1 minus x times, new parentheses, x minus 4, close parentheses, dx, negative 4.5, or the lovely fraction, negative 9 halves. And so we can check that we have the correct answer, which feels good. Okay, then let's take a look at part D. And in part D, the dx is across the top. I like to rewrite that to put it off to the side to help make it a little more recognizable. So we're integrating between 1 and the square root of 3 of 1 times, 1 over 1 plus x squared dx. dx on the top is the same thing as 1 times dx written this way. Now I need to figure out how to integrate this. It might jump out at you that this is one of the arc-trig function forms. It is. It's arctangent. So this actually will integrate directly into arctangent of x bounded between 1 and the square root of 3. So look at your derivative reference sheet until you see that. And now I can evaluate it. I can evaluate arctangent at the square root of 3 minus arctangent at 1. Okay, and I can have a little help from Desmos if I don't remember or just want a little help to evaluate arctangent of square root of 3. I might need parentheses. Arctan of square root of 3. And so it, of course, gives it to me in decimal form. I'm looking for an angle. And so if I divide off pi, that gives me pi thirds is my angle here. So this is going to be pi thirds minus, and then arctangent of 1. Now this one is easier to have memorized. You probably do. It's the one where sine and cosine are the same, and so that's pi fourths. But you could type in arctangent of 1, and you get, again, the decimal for it. It's some fraction of pi, so if you divide off pi, you can see it's pi fourths. Okay, and so then what I need to do is take pi thirds minus pi fourths with the common denominator. The coefficients are 1/3 and 1/4, so 1/3 minus 1/4 is the fraction 1/12, and so this combines down to pi twelfths. Okay, so my answer is pi twelfths in exact form. Now let's check it by doing the integral as a whole, and then we'll check it with the fraction value of pi fourths. So we wanted to do the integral from 1 to the square root of 3 of, I don't think it's going to accept dx over, but I'll try. So dx over 1 plus x squared. Yeah, doesn't like it. So I didn't expect it to, because dx closes the parenthesis for it. It does want you to rewrite off the side, so I expected that to need to be changed. So good to note. I hadn't ever tried it on top, so we tried it and did not like it like I thought it might not. And we're thinking that our answer should be pi twelfths, and they had the same decimal, so that sounds good. All right, excellent. All right, taking a look at the next page, we have a function that we want to consider here on the interval -3 to 1. Compute the following by hand using the fundamental theorem of calculus, including an appropriately drawn and shaded graph. Okay. Okay, so a bunch of by hand stuff. So the first thing to consider is that our function f of x is -x times x plus 3. And so that means that it goes through 0 and it goes through -3, and it is a parabola that faces downward. And so, because of the negative coordinate right there, and so I can just draw something right there, or if I wanted to, I could find out the vertex is going to be at -1.5. So if I wanted to plug -1.5 in to find out what the y value was, just to make my parabola a little prettier. Oops, wrong button. Come on, decimals graph, there it is. So if I wanted to plug in -1.5, oops, I'll square it outside the parenthesis, squared minus 3 times -1.5 gives me 2.25. So on my scale, 2.25 is going to be there, say. And so just as a rough sketch of what this part of it looks like. Okay, and we're actually bounded between 3 and 1, so I need to continue past 0 down here to 1. And so if I plug in 1, let's see, we can do that by just backing some things up, or we could do it by hand. It really is not that hard. We get -4. Okay, so -4 at 1. So my parabola, again, drops down like this. All right, and so the first thing to do is I'm making the appropriately shaded graph here, include an appropriately drawn and shaded graph. And so the area that we want is going to have some positive area in this region between -3 and 0, and then it's going to have some negative area between 0 and -1, or 0 and +1 right here. So we're going to have net area having this. So it's probably going to be some sort of small positive value. Since I have some negative, can I cancel with some of this positive? Okay. So that's what the graph looks like. Now we're going to set up the integral and find it. So we've got our lovely graph. So the net area is equal to the bounded integral between -3 and 1 of -x squared minus 3x dx. So using the fundamental theorem of calculus, I can do the antiderivative, and I'll get negative x to the third divided by 3 minus 3x to the second divided by 2. Add 1 to the power, divide by the new power. Bounded between lower bound negative 3, upper bound 1. Now we can evaluate. I'm going to go over here for some extra space. So negative 1 cubed, upper bound first, over 3, minus 3 times 1 squared over 2, minus negative 3 cubed over 3, minus 3 times negative 3 squared over 2. Some of the simplification we can do by hand, and so this first one comes out as negative 1/3 minus 3/2 minus, so this is going to have 3, 4, 5 negative, so this first one's going to be negative, and 3 cubed, 27 divided by 3 is 9, so it's going to be a minus 9. This one's going to have 2, 3, 4 negative, so altogether positive, and it's going to be 27. 3 squared is 9 times 3 is 27 over 2. Okay, so just again, wanting to get all this added up. Let's see, 27 minus 3 is 24 over 2, so that's 12 positive, and 12 minus 9 is 3. So this looks like 3 minus 1/3, so that would be 9 thirds minus 1/3 is 8 thirds. And at some point, grabbing a calculator might have given me a little more speed on that, but we've got ourselves a net area answer. So let's go ahead and check that one, and then on the next page, I believe we're going to be asked about total area. So we want to check that the integral from negative 3 to 1 of negative x squared minus 3x dx is 8 thirds. It's not allowing me to do a fraction. It doesn't always. It's just a matter of how it's computed, but that is 8 thirds. So good. That is our net area. All right. There we go. Made that a little extra big on accident. Okay, now we got to continue this example. Sorry, this one's running on a little long. This one is going to find the area, not net area. And so what they really should insert right here is the word total area. That's what they're talking about in this question. Find the total area. And so that's going to be of the absolute value of the function. And so if I draw my sketch again, I know that it had a already positive region. And then prior, it had the region that went down here to 1, negative 4, but we want to reflect that up here to 1, 4. Now this isn't completely straight, right? This would have been curving down there, so I tried to make it curving up there. It looks kind of straight, but it wasn't supposed to be completely straight. It's part of a parabola still. So it is still curving up there a little bit. Okay, and now our regions are both going to be positive. Okay. Now, I can't do these together because the first one is already positive. I'm going to have to separate this and do the integral as 2 pieces. I have to separate this right here at 0, the border between the already positive piece and the part that I need to turn into a positive. Okay. So the total area has to be separated to be the integral between negative 3 and 0 of our function, which was negative x squared minus 3x dx. And then we also want to add on the absolute value of the area between 0 and 1 of the same function. Okay, this part is negative, so I want to find out what it is, then take the absolute value and add it on. Another way of writing that, since I know that it's negative, would be, instead of having to keep the absolute values, which are kind of a pain, you have to get that fully simplified and then find its absolute value. Another way to write it would be to, I know that that integral is negative for sure, and so I can just subtract it. Since it is going to be negative, a subtraction is going to make it positive, and I'll be able to distribute the subtraction, and then I won't have had to worry about finishing that one little piece, then finding its absolute value, and not absolute valuing anything that's out here. So the subtraction kind of takes care of some problems there. All right, so breaking this down into the two pieces, first we're going to do the first piece that's going to be between -3 and 0. And so the antiderivative is negative, let me double check that I remembered that the function was correctly. Yes, looks good. So negative x cubed over 3 minus 3x squared over 2, bounded this time between -3 and 0. And then we have minus the same thing, so parentheses, negative x cubed over 3 minus 3x squared over 2, bounded between 0 and 1. Okay, so in the first piece, we have the upper bound is 0, so that's 0 minus 0, that's the first part of it, top bound, minus, from the bottom bound, negative 3 cubed over 3 minus 3 times -3 squared over 2. Okay, now at this point I'm going to take these negatives and just go plus, right? Make it all plus, distribute that negative to say plus right here, and then we're going to have our 1 cubed over 3 plus 3 times 1 over 2 minus 0 minus 0 when I plug the zeros in. Okay. All right, and then we have, okay, 3, 4, 5 negatives. This part's negative 9. And then 2, 3, 4 negatives. This part's positive 27 halves. Plus 1/3 plus 3 halves. Okay, so I have 27 plus 3, that's 30 halves, so I have 15. 15 minus 9 is 6, and then 6 plus 1/3 is 18 thirds, plus 1/3 is 19 thirds. So I have 19 thirds for our solution there. Okay. Now, last thing, let's just try to check this one. Now, I believe that on decimals, we can check it with having the absolute value. It's just not something I can integrate by hand. So if I go from -3 to 1 of the absolute value of negative x squared minus 3x dx, I get that decimal for 19 thirds. So I can have decimals check it. Again, I'm doing the absolute value of the function. When I'm doing it by hand, I can't integrate an absolute value function. So by hand, I have to integrate it piece by piece. So maybe even above up here, I could write what I wanted to do, which was the integral from -3 to 1 of the absolute value of the negative x squared minus 3x dx. And decimals is able to take that in as an argument, but by hand, I have to separate it into the two pieces without the absolute value so that I can get them integrated.